So welcome back to the last talk of the afternoon session. We have with us Anurag Rao from Technion, who will speak on dynamical questions arising from Dirichlet's theorem on Diophantine approximation.
Thank you. First, happy birthday, Professor Dani. Thank you to the organizers, all the organizers. I'm very happy to be here and to see everyone. This is a great conference. So this is about dynamical questions arising from Dirichlet's theorem. I promise at the end, I will show you a theorem, a new theorem. But I think it's also maybe important to give some motivation and context. So we saw a bunch of talks on Dirichlet's theorem by Anish, Shah, Kleinbach, Shucheng. I also want to continue that theme and somehow explain how Dani's correspondence relates Dirichlet's theorem to the dynamics of sphere packings. So this is Dirichlet's theorem. What's going on? We have a real number and alpha, and we iterate by integers. We take q alpha, and then we look at the distance from q alpha to the integers. And Dirichlet's theorem says to get within 1 over t of the integers, you need to go by less than t. Okay. This constant 1 over t. So first of all, you can prove it maybe by using the pigeonhole principle. But the constant 1 in this 1 over t can be changed to anything larger, and the truth of the statement would remain. So in what sense is it optimal? Well, that was addressed by Davenport-Schmidt. Okay, so what they did was they tested when the system would be solved for some c less than 1. So again, instead of 1 over t, we have c over t. We want to see whether there are any alpha for which this system can be solved in p, q, and z for all sufficiently large t. So there's a lot of quantifiers here, but they gave this definition, the set of Dirichlet-improvable numbers, written di, which is the set of all, real numbers alpha, such that this system, alpha q minus p less than c over t, or 0 q between 0 and t, can be solved for all sufficiently large t. Okay. Feel free to stop me if you have questions. And here's what they proved. This Dirichlet-improvable set has measure 0, but it has full Hausdorff dimension. Okay. What's next? Yeah, the union goes up to full dimension. Yeah. Okay. So they had this characterization of the set of Dirichlet-improvable numbers, which was that alpha is in Di, alpha is Dirichlet-improvable for some constant, so that is some constant c. So that implies that either alpha is rational or it has bounded digits in its continued fraction expansion. So those numbers that have bounded digits in their continued fraction expansion is exactly the set of badly approximable reals that we've seen again and again, especially in Erez's talk. So these are the numbers alpha for which there's some c greater than 0 such that this system has no solutions. Okay. So the story is that they gave this characterization of Dirichlet improvability, and then in an earlier paper, Schmidt had shown that, as we know, Schmidt had shown that BA has full dimension by inventing his Schmidt game. So in his 1966 paper, Yeah, we saw in Erez's talk this game. So again, I'll say it again shamelessly. Okay, so it's played on a complete metric space XD, and you have a target subset S, and parameters alpha, beta between 0 and 1. Bob chooses a ball D0, and then Alice and Bob keep trading off by choosing balls within the previous balls, but you have to shrink your radius by the ratio alpha and beta respectively. And if the intersection is in the set S, then Alice wins, otherwise Bob wins, or maybe that's not important. So S is said to be winning if Alice can produce a winning strategy for some alpha, and Bob is allowed to vary beta. So if there exists some alpha such that Alice has a winning strategy for every beta, then the set S is alpha winning. Okay. So yeah, Schmidt proved that there's a winning strategy for alpha less than half for BA. And then winning sets, as we know, have full dimension, are closed under finite intersection. Although if you have an uncountable number of alpha winning sets, then the intersection is also winning, and they're preserved under Lipschitz maps. Okay, so summing up what Davenport-Schmidt did in their paper, I guess, is that they proved dA is a subset of DI, or they proved DI is exactly BA union Q. And then that's how they saw that this Dirichlet-improvable set has full dimension. They did a similar theorem where they were looking at Dirichlet's theorem for forms. And they didn't have a perfect characterization of this DI set, but they again proved dA is contained in DI. And so you get this theorem that Dirichlet-improvable numbers or vectors is a large set. Okay, so yeah, I want to maybe just highlight some dynamical arguments implicit in all of this, and then maybe speak about some new questions that you could ask. Okay. Okay, so let's say we want to prove a Dirichlet theorem for the Eisenstein integers. Okay, so the setting has changed a little. I hope you'll excuse me. So now I'm looking at complex numbers. So alpha is a complex number now. And I want to see if there's a constant C, like maybe the one in Dirichlet's theorem, such that I can solve this system, alpha q minus p, absolute value less than C over T. So the absolute value over here is modulus in complex absolute value. So that's different. And I want to see whether you have solutions for P and Q in the ring of Eisenstein integers. So, so this J that I've written there is this third root of unity. Okay, that's what it is. Okay. So yeah, okay, so I want to highlight this Dani correspondence thing. So let's see how to do this. Okay. Some notation. Yes, I'll do Gaussian later. Yeah, yeah. So first I'll do Eisenstein, then we'll talk about Gaussian integers. Okay. I mean, it's just it's as much motivation as the Davenport-Schmidt Dirichlet-improvability. I don't know. It's something. I just want to highlight the Dani correspondence. So it's something new, and you can apply it here. So yeah. So maybe you want to look at good approximations of complex numbers by P over Q, where P over Q are coming from some number field. And maybe some people in the audience have done work or are interested. Yeah, okay. But you're right. There are many cases in which you could study this. I just picked one, and let's just go through the argument for this case. Okay, so the key point is that this solvability of this system is actually equivalent to some set theoretic intersection being non-trivial. So the notation I want to use is this lambda alpha j. Okay, so lambda alpha j is this matrix applied to this discrete subset of C2. Now, maybe I should point out Zj times Zj is it's a lattice. It's not a covolume 1 lattice. It has covolume 3/4. So, and you're applying something which has determinant 1 to it. So it's some lattice. It doesn't have covolume 1. Okay, just to point out. And then B infinity 1 is a product of disks in C2. It's just the soup norm ball. Okay, so I hope you see that this thing having a non-trivial solution, or this thing having a solution, is equivalent to this lattice intersecting this dilated ball non-trivially. So, okay, so if you can imagine C cross C, you're applying this transformation to the soup norm ball, and then you want lattice points in here. Okay. Okay. Now, yeah. So one trick you can play is you can try to normalize things so that this matrix becomes diagonal, and it does so exactly if you choose S to be natural log T over square root C. Okay, so I should mention all of this is like a thought experiment. We want to see if such a C does exist. So bear with me. Okay, so this condition with some fixed C is equivalent to multiplying through by this diagonal matrix, e to the S, e to the minus S, where S is a function of T and C. Okay, and that has the effect of turning this stretched shape into something that has, equal length on the coordinates. Okay. So you can rewrite this as GS times lambda alpha j intersection B infinity square root C is non-trivial, where GS is this diagonal flow. Okay. Okay, so the existence of a C which will make this intersection non-trivial is pretty clear, because we have Minkowski's convex body theorem, which says that in R4, if you have a symmetric convex body which has volume more than 16, then it has to intersect the standard lattice non-trivially. So you can apply the same thing here and say that if this volume is greater than 16 times this co-volume, then you will always have a non-trivial intersection, so that Dirichlet system can be solved, and you're done. Okay, so you can cook up this constant. So you see that if you have C greater than about 1.1, you do get a Dirichlet theorem. But the point is, okay, yeah, so in case you're confused, again, yeah, I wanted to point out that co-volume of this thing is 3/4. Okay, so that's how you solve for C. And then you get a constant, but it's not an optimal constant. So the optimal constant turns out to be 1 again, and this is Dirichlet's theorem. This is it's a very nice theorem. Okay, so it's exactly the same theorem as Davenport and Schmidt's theorem. So for every complex number, for sufficiently large T, you can solve this system for P and Q. So there should be like a bracket here, or I should remove the square. Yeah, P and Q Eisenstein integers. And again, we can make the same definition of Dirichlet-improvable complex numbers. These are the set of alpha and C, such that for some C less than 1, this exact system with 1 replaced by C less than 1, can be solved for all T sufficiently large. Okay, so I'm claiming something here, right? So I'm claiming that Dij has Lebesgue measure 0. However, it's large because, again, it contains the set of badly approximable complex numbers with respect to the Eisenstein integers. So again, we have this almost the same definition as in the real case. Badly BAJ is the set of complex alpha such that there's some constant where you can't have really good approximation. So alpha q minus p times q less than c has no solutions. Okay. Okay. So yeah. Okay. So let's see how to go through this. So remember the key. Yeah, the Dani correspondence is that system about Dirichlet improvability is, or Dirichlet's theorem is solvable if and only if you have a non-trivial intersection of this lattice with this ball. And again, remember that GS denotes the diagonal flow and lambda alpha j denotes this lattice. So what we're actually looking at here is, I want to look at the set of Eisenstein lattices in C2. So what I mean is they're going to be ZJ. So the definition is I'm going to look at ZJ submodules of C, discrete ZJ submodules of C, which have finite covolume. Okay, so I don't want to look at all of them. I just want to look at a smaller homogeneous space, which will at least contain all of these guys. So I'm going to define xj to be SL2C or SL2ZJ, and I identified this with some subset of Eisenstein lattices by just taking a matrix M and taking ZJ combinations of the columns. So that will give me an Eisenstein lattice. Okay. Right. So the nice idea here is you want to see the optimal constant C for which this will always have non-trivial intersection. So you can just think about a constant C that works for the entire homogeneous space xj. So this is nice. I mean, xj of course contains all of these. You'll see that it is invariant under GS and it has a probability measure. Okay, so it's not the set of all Eisenstein lattices, it's some subset that we can work with. Okay, so we're going to define this critical radius. It's going to be the supremum of R such that there exists some lattice in xj with some lattice lambda with lambda intersection b infinity R trivial. Okay. Right. So Rj is the supremum. You can see it's finite. And the point is that if C is greater than Rj squared, then this will always have non-trivial intersection, just by definition of Rj. Right. Okay. So it turns out that this Rj squared is actually the optimal constant for Dirichlet's theorem. So abstractly, I'm telling you there does exist some constant for which Dirichlet's theorem holds. But we, of course, have to do other things in the theorem. We have to show that it's one, so on and so forth. Okay. So with this, along with this Rj comes the critical locus. I'm going to call it Lj. It's the set of all lattices which intersect B infinity Rj trivially. Okay, so it's non-empty because, if Rn converges to Rj, you can find a sequence of lattices lambda n which intersect those balls trivially, and then you can use Mahler compactness criteria to show that these lambda n's have a limit, and it lies in this set. Okay, and then you also have a system, a very natural system of neighborhoods of this compact subset, which is LJR. So it's a set of all lattices lambda and xj, which don't have two, they don't have a very short vector or a vector shorter than R, length R. Okay. Yeah, okay. So with all of this consideration, the point I'm trying to make is that it's very easy that the set of Dirichlet-improvable complex numbers has measure 0. Okay, so let's try to go through that. So the key is that this GT, or this diagonal action on xj, is ergodic. In particular, almost every lattice is going to be dense under this flow. And not only that, but almost every lattice on this expanding horocycle is also going to be dense under the flow. Okay. Yeah, so that's using ergodicity. You can see that for almost every complex number alpha, there's a sequence of unbounded times Sn such that Gsn lambda alpha j converges to something which lies on this critical locus, some lambda which lies on this critical locus. Okay. So that means given any c less than rj squared, for almost every alpha, there's the sequence of unbounded times for which, well, okay, if you're converging here, you're going to lie in those what neighborhoods? Yeah, in these neighborhoods. And that means, yeah, you have a trivial intersection here, which exactly translates into this thing, again by the substitution, having no solutions. So, okay. I hope this is kind of clear, but yeah, it's just ergodicity will show you that almost no alpha is Dirichlet improvable. Okay. So, but there are still some things left to show in this theorem. Okay, so yeah, so summing up, we've shown the existence of an optimal constant Rj or Rj squared for which Dirichlet's theorem holds, and we've shown that if you redefine Dirichlet improvable with this constant, almost no alpha is Dirichlet improvable. And incidentally, if you go through whatever we've done, we actually have a characterization of alpha belonging to Dij. So alpha is Dirichlet improvable if and only if Gs lambda alpha j, where S is positive, this trajectory eventually avoids a neighborhood of the critical locus. Okay. And then to what's remaining is that we need to show that this constant is 1. Badly approximable numbers j have full dimension, and dA is contained in Dij. So this will complete the exact analog of Davenport-Schmidt's theorem. Okay, so Daj is winning. Okay, so we've heard a lot about these winning arguments. So I guess the first time, so this paper of Estalschu and Christensen showed that Daj is actually winning, and they used a similar strategy that Schmidt used to show that the normal dA set is winning. Okay, and they proved the same thing for other rings of integers, Zi, Zj. Okay, but as Erez mentioned, you can prove questions. Okay, yeah, you can prove winning in different ways. So maybe this is a good point to remind ourselves of Dani's correspondence. I mean, another version of it. Right. So yeah, so let me remind you, you again have the same thing, almost the same proof, which is that alpha is badly approximable j in badly approximable j if and only if this thing, this orbit, this forward orbit of lambda alpha j is precompact in X. So I'm going to use precompact and bounded interchangeably. But again, this is Dani's correspondence. And yeah, I guess Erez did reprove this, prove it in his talk, and it's exactly what we were doing before, just some renormalization. You have to choose the time correctly, I guess. Okay, so yeah, so there's many ways to probably see that this is winning. In any case, I guess Estal, Shu, and Christensen were the first people to show it, and they showed something more general anyway. Okay, so it's left. We still have to show Rj is 1 and dA is contained in Di. Okay, so let me just highlight. We have two dynamical characterizations of these number theoretic sets. So alpha in Bj if only if this orbit is precompact, and alpha is in Dij if and only if this orbit avoids this critical locus Lj. Okay. So these two things remain. Recall the definition of Rj, the critical radius and the critical locus. So this is where, I guess sphere packings come in. So if you look at the definitions of these things, Rj and Lj, and you think about it a little, you see that answering the questions, what is Rj and what is Lj, corresponds exactly to solving these things. So in the space of all Eisenstein lattices, GL2C mod GL2J, which of them give the densest packing of C2 by this domain B infinity 1? So B infinity 1 is product of disks. So maybe I lied to you. We're not doing sphere packing. We're packing product of disks. So, okay, it's still okay. Fashionable problem. Okay, and the second question. So I guess that will answer what Rj is, but I mean you should answer both of these simultaneously. The second question is that all of these, the things that witness the densest lattice packing, will have a certain co-volume. You can rescale your ball so that you can arrange those lattices to have determinant 1, and then you can intersect it with this subhomogeneous space and ask, what does this set look like? And that'll exactly, correspond to answering what does this set look like. Okay, and we don't have to do any work for this. It's already done more than 100 years ago. So I guess Xu Cheng was talking about, Hayosh theorem and effective Hayosh theorem. There's an exact analog in the dimension 2 case for Eisenstein packings of disk cross disk. So so Minkowski proved this. He was trying to, of course, he was studying a linear forms theorem, and he proved that Rj is 1 and Lj is exactly these two sets. Okay. Okay, so I guess okay, good. So a sanity check. What this is saying is that the solution to this problem is that the best lattice packing of we have to renormalize to make sure they have the right determinant. The best lattice packing of or the best Eisenstein lattice packing of B infinity 1/2 is by the standard lattice, just a product of Zj. And that should make sense, because if you ask what is the best lattice packing of the disk in C, that's exactly witnessed by this hexagonal packing, by the lattice Zj in C. Okay, so it's also conjectured that this is the best lattice packing over all lattices in SL 4R mod SL 4Z, but we don't really need that. Okay. So that's the reason we have this nice description of the critical locus. In some sense, it decomposes as a product, because because Zj is the best packing of the disk. Okay. Yeah, this is a picture from Minkowski's manuscript. Okay, he proved it. Yeah, whatever. Okay. So, okay, now maybe I can highlight some dynamics. The last thing to show is that, why is BAJ contained in DIJ? Why is bad contained in Dirichlet? So again, let me remind you, alpha is bad if and only if this trajectory is pre-compact in X. And alpha is Dirichlet improvable if and only if this trajectory avoids a neighborhood of the critical locus. So the crucial observation, in case you haven't already noticed, let me go back, is that everything here, every single lattice here has a divergent orbit under the diagonal slope, either in the forward direction or in the backward direction. So every lattice here, it contains a vector on the x-axis, so I guess it's backward divergent. And every lattice here has a vector on the y-axis, so I guess it's forward divergent. Okay, so that's essentially what Davenport and Schmidt were implicitly using, except that they didn't have the Dani correspondence. So, okay, so we do. So we can rewrite their argument in one line. Okay. Okay. So if I take an alpha and bad, it has a bounded orbit. Why does it avoid the critical locus? Well, it has to, because if there's some subsequence along which lambda alpha j converges to something in the critical locus, I can translate by GS and see that, along another subsequence, it has to converge to GS lambda. But this thing is going off to infinity. So that can't happen. That's it. Just, yeah, one line. Okay, and I'm also talking about limit points of lattices, lambda alpha j. So when I say limit point of an orbit, I mean there's a sequence of times Tn going to infinity, such that lambda 2 is a limit point of lambda 1 if there's a sequence of times Tn going to infinity, with GTN lambda 1 converging to lambda 2. Okay. Okay. So I've shown you this beautiful Dirichlet theorem for the Gaussian, the Eisenstein integers. Now I'm going to show you the scuffed version of Dirichlet's theorem for the Gaussian integers. Okay, so again, so of course you can ask an uncountable number for an uncountable number of Dirichlet theorems. But here's the Dirichlet theorem for the Gaussian integers. It's not so nice. And one of the reasons is that the Gaussian integers, Zi, is just the standard lattice Z in R2. And that does not pack the disk efficiently. So, okay, so that's some kind of heuristic, but okay, you get exactly the same theorem with a weird constant. Again, it's very easy to just using ergodicity to show Di has Lebesgue measure 0. And you can also show its full Hausdorff dimension. So I'll comment on this. But first, this is what the lattices, the Gaussian lattices, which witness the best packing of disk times disk is. It's this awful set. So this turns up because, well, the norm or the convex body is invariant under this. This is cooked up to make the determinant 1. So what's really going on is something here. Okay, again, this is theorem of Minkowski. And yeah, the optimal Gaussian lattice packing of disk times disk is not as good as the optimal Eisenstein lattice packing of disk times disk. Okay. So yeah, so I'm trying to point out that, okay, so where does dynamics come in? So in one case, I had an obvious property of the critical locus. In the second case, I mean, what do I do with this? I know nothing about this set. I can't really prove. The BA contained in DI argument just completely breaks down. You can still prove that DII, this Dirichlet-improvable set, has full dimension, you have to use a different kind of winning argument due to Arndt-Kleinbach, which Erez spoke about. But yeah, the connection with bad is lost. And I guess, you know, I mean, somehow I've made a career out of proving Dirichlet theorems and saying, you know, some set is winning. And then sometimes I'm saying, oh, it contains bad, so it's winning. And sometimes I'm saying, oh, by Arndt-Kleinbach, it's winning. And I guess this is a question of that Barak at some point asked me, although he doesn't remember it. And other people, they said, you know, what is the relationship between bad and Dirichlet? So, well, we took your comments seriously. And essentially, it comes down to answering this dynamical question. Okay, so when exactly is bad contained in Dirichlet? In other words, bad is bounded orbits. Dirichlet is avoiding a critical locus. So if you want bad and not Dirichlet, you need to construct bounded orbits with a limit point, with a certain limit point in the critical locus. So this Davenport-Schmidt Dani whole number theoretic consideration shows that there's an obvious, so the question is, when can we construct a large number of precompact orbits with a prescribed limit point lambda naught? So this whole Davenport-Schmidt Dani thing shows that there's an obvious obstruction to this. So if lambda naught has an unbounded R orbit, it's impossible to construct bounded orbits with this limit point. On the other hand, if you do have lambda naught with precompact R orbit, can you construct bounded orbits with that limit point? So, okay, it's not so interesting, but it's a question you can ask. Yeah, people are interested in bounded orbits, so why not this? Okay. And okay, so we finally have our theorem. So in SL2R mod SL2Z, that's the only obstruction to constructing bounded orbits with a prescribed limit point. So the theorem is, if you start out with this lambda naught, which has precompact R orbit under the diagonal flow, then you can construct a full Hausdorff dimension set of lattices. I'm just calling it set lambda. So well, we construct a full dimension set on the expanding horocycle at Z2. But that doesn't matter. So you can just, that implies a full dimension set in X. And this set of lattices has the property that the forward orbit is precompact and lambda naught is a limit point of lambda. Okay, and if you look at this set, it does not have the winning property. So, okay, unfortunate or not, I don't know. It just does not. Okay. And a sketch of the proof. You construct a transversal, a Poincaré section. You construct your favorite section for the geodesic flow on X. You have your desired limit point lambda naught. Without loss of generality, you assume it's on the section. I guess, okay, so if you know, well, okay, you probably, if you pick your favorite section, you'll probably see that it's isomorphic to the shift map. X is SL2 R mod SL2Z, like exactly what was in the previous talk. So yeah, so it has a section that in some sense preserves some of the topology. So if you take a bounded orbit lambda naught and you move it to the section, you get a bounded function from Z to N. And in order to construct lattices lambda alpha, so I haven't told you what lambda alpha is, but it's just the set of these lattices. So if you want to construct lattices of this form, which have lambda naught as a limit point, all you need to do is make sure that in the continued fraction expansion of alpha, you see these stabilizing blocks. I mean, these blocks which stabilize in both directions. And then, okay, this is a condition, it defines a set of alpha. And if you make your condition sparse, if you say that, okay, I want these blocks to appear, after with enough spacing, you can see that what you've constructed is a very fat Cantor set, and then it has dimension close to 1. And yeah, that's it. Okay.
Questions or comments?
How do you know the set you're constructing is not winning? You said that as a remark.
That's due to Angwan and Kleinbach. The complement is winning. So the set of the bounded orbits, which do accumulate on a certain point, which do avoid a given point is winning. So, yeah.
Thank you for the great lecture. Can you also have a geometric argument rather than the symbolic dynamics argument by stable foliation? So don't they have to be on the same stable foliation, your x naught and your sequence? I'm just wondering. I mean, this is perfectly fine, but can one avoid symbolic dynamics?
Maybe, but I don't quite follow what you said about the same foliation.
It's a question.
Okay.
Does a lambda naught,
you're looking at its endpoint,
sequence have to be on the same stable foliation? Because if it's a limit point,
yeah,
they have to get close somehow, right?
Yeah.
Infinitely often. So doesn't that imply that they have to be on the same stable leaf?
So you're doing a lower upper decomposition of lambda naught? Is that what you're doing? I don't understand. I mean,
I'm just thinking geometrically.
Okay.
I don't do any decomposition.
Okay, you don't.
Maybe we'll talk afterwards.
Yeah, we should talk. Yeah.
If not, let's thank Anurag.